Last time we took a look at Young's experiment, which is also known as two-slit or twin-slit diffraction. Now here I want to introduce a experiment due to a fellow by the name of Lloyd. And the experiment's known as Lloyd's mirror. The idea is you have a mirror like this, and you got a screen here. Now what you do is you put a light source just right there, pretty close to the mirror, like so. Now, if I look at some point on the screen, like let's just say right here, there are actually two paths that light can take to get there. One is the straight line path. The other one is the path that you get when the light bounces off the mirror, like so. Now, when we do ray optics, what we will see is that this angle here and this angle here are the same. So light just bounces off of the mirror just like a billiard ball would off of a cushion in the table. But what this means is that this would, optically speaking, this is the same difference as if instead of there being a mirror there, we had another light source right here. And we can say that the distance between these sources is d. And if you take a look at this, in a certain sense, this is just like Young's experiment. We've got a slit source of light here, and this other path that we take is as if we had another light source right there. So one slit, two slits, effectively. Except there's one big difference. And that is that the interference pattern that you see in Lloyd's mirror, and you do form an interference pattern on the screen, is the opposite of Young's experiment. So by that I mean everywhere in Young's experiment you had a bright fringe. In Lloyd's mirror you have a dark fringe. And everywhere you had a dark fringe in Young's experiment, in Lloyd's mirror you have a bright fringe. So it's the exact opposite. So as a pause and ponder moment here for you, I want you to think about what this means about what's happening with the light that's bouncing off the mirror. So go ahead and pause the video for a moment and then get back with me on that. So what this means is that the light that reflects off of the mirror reflects off the mirror, flips upside down. By that I mean if you had a crest, it's now a trough, and if you had a trough, it's now a crest. The fancy fancy physics jargon way of saying this is that you have a 180-degree phase change. But all that means is the light that hit the mirror, if a crest hit the mirror, when it reflected off the mirror, you had a trough, and if you had a trough when it hit the mirror, it reflected back with a crest. And we have seen this kind of thing before with mechanical waves. So just as a quick reminder with mechanical waves, if I had an end that was fixed like so, if I had a pulse come in like so, when it would reflect back out, get reflected back out upside down. And if the end was free, so say, a ring with a little rod that it's free to slide up and down along like that, then if the wave came in as a crest, it reflected back out as a crest. And it didn't have to be this crazy. It didn't have to be a flat out fixed or free end. What you could have had was just simply, say if you had thin rope, so for instance here, you could have had like a thin rope and then a thick rope like that. The wave speed was faster here, I'll say V1, and the wave speed through this bit of string here is slower. And so when you change from faster to slower, you reflect back upside down. On the other hand, this situation, you also get if, say, you had something like an interface like this, where here the wave speed is slower in this part than it is this part, like so. The wave that reflects back off of the interface here would reflect back right side up. So for light, what does that mean? What this means for light is that if we had, say, two media here, we'll say index of refraction N1, index of refraction N2, like that. If the wave is going faster through N1, through material number 1, than it is material 2, does that mean that the index of refraction is higher or lower for N1? So go ahead, pause, and get back with me on that. That's right. If the wave speed is faster, that means the index of refraction is lower. So following our analogy here from the mechanical wave, if we have light that's propagating through a lower index material, and then it comes up against a higher index material, here the speed of light is faster, here it's slower through the material. There will be light that reflects off of this surface, and that light that reflects back will reflect upside down. That is what was happening with Lloyd's mirror. If we go back here, the material here is air. It could be a vacuum for all it matters, because remember, the index of refraction of air is only slightly bigger than 1. And a vacuum would be 1. And the mirror, it depends on the details of the construction, but if we just say it's a piece of glass, that would do the job. Typical value of index of refraction for glass is usually 1.33, although that depends a lot on the recipe of the glass that's being used. So the light was in a lower index area here. So here the light is at the index of refraction here is roughly 1. And here, we'll just say if it's glass or something like that, 1.33-ish. Something like that. The point is it bounced off of a higher index. And since it bounced off a higher index, if we had a crest, over here now we have a trough, and vice versa. Now, just to complete the analogy here, if we go the other way, so if N1 is greater than N2, so the light is traveling slower in this material than it is this material, what that'll mean is the light that reflects off of the surface. So some will go through, some will reflect, just like over here with the mechanical waves. The light that reflects off of the lower index material and heads back that way will reflect back right side up. So this gives us an application of, it's called thin film interference. And a good example of it actually is if you have your cell phone handy, take a look at the camera on it, the camera lens. If you look at it carefully, you'll see that the light that reflects off of the camera lens, depending on the design choice that the manufacturer makes, will either have a bit of a reddish cast or sort of a bluish greenish cast to it. And this is due to coatings that they put on the lens. Now, the main point of these coatings is actually to help coax light forward through the lens, but we'll get into that in a little bit. But for now, let's just think about the possible scenarios that we could be having here in thin film interference. So for instance here, we can be thinking about things like, say, having gasoline, if you, like for instance, a soap bubble or something like that, or like say a gasoline slick sitting on top of water in a parking lot after a rain, anything like that. Well, it turns out that we'll have some medium here, could be air, could be something else. Then we'll have another medium here. This is the medium for the thin film itself. And then you will have an index of some other medium here. This is whatever the thin film is sitting on top of. So for instance, if you're blowing a soap bubble and you see all the shiny colors coming off of the soap bubble, what we would be having here is air, soap film, air, as an example. Now, so we can predict we can figure out what wavelengths of light are apt to be reflected back strongly by thinking about the possible paths that the light can take as it comes in. So say we have light coming in down on our thin film like so. Oops, that's pretty badly drawn. Pardon me a moment here. There. So I'm going to have to draw this at a very slight angle. Well, we'll just do it like this. So we have light coming in. Now, what's going to happen here is that some of the light is going to reflect right off. And it'll reflect straight back up, but the drawing will get really cluttered. So I'm just going to displace it off to the side like that. So some of the light gets reflected. That also means that some of the light gets transmitted into the film. I'll just say goes into film. And then we get to this surface, and it's going to be the same deal again. Some of that light will get reflected, and some of that will get transmitted. Now, what the deal here is the light that got reflected off of this surface, that's this bit here, and the light that got reflected off that lower surface, that's this bit here, these two bits of light are going to interfere with each other. So, how are we going to get, let's figure out how we can get constructive or destructive interference here. So if I So here we'll say, we'll make this, we'll call this case 1 here. And with case 1, we have two possibilities. We could have that each index we reflect off of is progressively lower. Now, if we do that, there will be no phase change at either surface. Let's try that again. There. No phase change there. Here or here. So now, if I'm looking down here from above and I want constructive interference, which means that I will see that color. I'll see that color. It'll be a bright. It'll be a relatively bright reflection off of that surface. What's going to matter is the round trip distance that we make through the film. So if we say the film is of thickness t, this bit of light right here, boink, boink, made it traveled an extra distance to t. T down like that, t up like that. Now, if that round trip distance is an integer number of wavelengths, then if I had a crest here, I make a round trip. If that round trip is, say, 1 wavelength, I'll have a crest that reflected off here, and this will be a crest coming back up like that. So the 2 bits will have crest meets crest or trough meets trough, whatever. So we'll say an integer number of wavelengths. Now we have to be careful. It's the wavelength in the thin film. So remember, the wavelength in a material will be the wavelength in vacuum, or basically air, divided by whatever you're traveling through, in this case, the thin film. So because light is traveling slower, the index is, traveling faster here, the wavelengths would be longer in this case than it was here. So that's something we have to account for if we're going to come back and have crest meets crest or trough meets trough. Now there's another possibility. The other possibility would be, so let me just go ahead and redraw here. So for our same thin film like this, N1, say N2 greater than N1, N3 greater than N2. Now, what's going to happen here, and now I'm going to draw at a very slight angle just to declutter the drawing a bit, but you should understand that I'm still thinking about this as just straight up and down. So this is really up and down. I'm just offsetting a bit to declutter. So now here, when the light that gets to this surface, some of it is going to pass through and some of it's going to get reflected. Now, the stuff that gets reflected, because it's reflecting off of a higher index where the speed of light is lower, what's going to happen is you're going to have a 180-degree phase change on the light that got reflected. So by that I mean if I had a crest come in and hit the top part of the film, I now have a trough reflecting back off. And if I go take a look at the bit that's going through the round trip here, so this passes through, some of it will pass through. We don't really care about that for this. And this bit here, because it's bouncing off of higher index, will again have a 180-degree phase change. So here I would have had a crest that got turned into a trough. Well, since they both had crests that got turned into troughs or troughs that got turned into crests, there's no difference from an interference perspective. And again, we would have constructive interference. In other words, you'll see the color that gets shined on here brightly. Either way, this, near as I can tell, and since the Bureau of Engraving and Printing isn't exactly talking about everything they're doing, if you take a look at U.S. currency, any bill $10 or higher, the number in the lower right-hand corner will change color as you tilt the bill back and forth. And what that's, I think that's this case here. This material will be air. The color shifting ink will be some index greater than air, and then sitting on top of paper or something, and that would be an even higher index. So you would have a phase change here, phase change there. That's that color shifting number. Now, why is the color shift? And that's because I've been looking at this just at the straight up and down case. If you look at the number and angle, then the round trip distance through here will be longer because of the fact that you're at an angle. And so that will change what wavelengths will have constructive interference, which will mean the color that you see. Now, how about the color that you don't see? That'll be destructive interference. And here, to get destructive interference, it's just going to be the same kind of deal. You will need an odd half integer number of wavelengths in the thin film, so m plus a half. So here, m is 1, 2, 3, and so forth. Here, m is 0, 1, 2, 3, and so forth. We can't have m equals 0 here because you just literally have no film. But in m equals 0, you get that the thickness of the film is 0. That doesn't make sense. I mean, it might mathematically make sense, but physically it doesn't make sense. So we have to exclude the 0 case here. Now, there is a different scenario. This is why I called case 2. And case 1 and case 2 are my names for this. Other people call them something different. But anyway, so this is case 2 here. And here, so in case 1 is when you had either no wave changes or both surfaces had a wave change, or had a phase change. Case 2 is going to be a case where one surface has a phase change and the other one does not. So the two possibilities here would be, again, we'll say that the thickness of the film is T. N1, N2 less than N1, and then N3 greater than N2. You can make this, it's kind of fussy it's kind of hard to do with modern microscope slides, but if you can find old ones that aren't tempered, you can take a little bit of onion skin paper, put it on either end of a microscope slide, so you get like glass like that, and you can, as you push up and down on it, you'll see the color of light passing through there change. Unfortunately, tempered glass for other reasons kind of messes that up, but that's a possibility. So say you have some sort of an air gap between two pieces of glass, that would be an example of this. So in case like this, the ray that comes in, again, remember, I'm really thinking these as really straight up and down. I'm just drawing them at a bit of an angle to declutter the drawing. So there would be no phase change for the light that bounced off the top surface, but for light that passed through. For the bit that reflects off of this surface here, there will be a phase change because you're reflecting off of the lower index. Or the other possibility we can have, and this would be, say, like a soap film or something like that, N1, N2 greater than N1, N3 less than N2. So this is a soap bubble. Air, soap, air. The light that reflects off of the upper surface of the thin film will have a 180 degree phase change. Now, some of this will pass all the way through, but for the bit that reflects off of the lower surface, there will be no phase change. So in this case here, what winds up happening is we flip the constructive and destructive, just like Young's experiment versus Lloyd's mirror, same kind of deal here, because only one of these is having a phase change. If neither had a phase change, then say if I had a crest here and the round trip gave us a crest to get constructive interference, now because of the phase change, it'll flip and we'll have a trough, destructive interference. Or for instance here, crest came in, bounced off of this and inverted into a trough, which it would not have done otherwise. So if this comes around as a crest over here, it would instead meeting a crest, because only this surface changed phase, the crest now meets a trough. So this has the result of flipping which is constructive and which is destructive interference. So in these case 2 situations, constructive interference will happen when the round trip distance is m plus a half times the wavelength in the medium, in the thin film, so lambda over the index of the thin film. And again here, m can be 0, 1, 2, 3, whatever. And for destructive interference, the round trip distance will be an integer number. And again, we can't have 0 simply because that would mean that there was no film at all, and that wouldn't make any sense. 1, 2, 3, and so forth. All right. We'll do an example in a second here to help make this a little more concrete with numbers, but I just want to go back and think about the coatings on the lenses that I was mentioning earlier. Depending on the choice of coating, you could, the optical designers will usually put together an artfully arranged collection of coatings so that what they can do is that at, say, the front surface of the lens, where normally some percentage of the light, could be as much as a quarter of the light, would bounce off of the front surface of the lens and not make its way to the sensor in the camera, which would be just a waste. They put the coating on to encourage destructive interference. Now what they do is they actually have a whole artfully arranged stack of coatings so that what they can do is they can have destructive interference for almost all the colors of visible light, but they usually can't get it perfect, and so you'll end up with some constructive interference that the engineer will design to be either on one side of the spectrum or the other. So thus, when you look at a camera lens, you either get sort of a bluish reflection, or you get a green, or you get a reddish reflection. And so what that means that there will be some loss of light in that particular color region, but that's something that they'll calibrate into the interpreting the sensor, the data from the sensor on the camera. But by doing this, they can coax most of the light forward simply because you have destructive interference on the reflected light, which means that there is no light going back, it forces it forward. And this is actually really important because it isn't just the one surface on the lens. Each lens has two surfaces, a front and a back. So you get light could be reflecting away from the sensor on each surface. And with the exception of cell phone cameras, which are where they have very artfully designed teeny tiny little lenses, most camera systems at a minimum have three or four lenses in them. This has to do with managing effects, an effect called chromatic aberration, which we'll get into later. And some some lens systems could have as many as eight or 10 lenses. And so that could be as many as 20 surfaces. If you kept having light reflect away from the sensor at each of those surfaces, you would have very little light making its way through. So the coatings are very important, and it's part of what makes good camera lenses expensive. Now, the cell phone camera, you typically have one, maybe two lenses. So you'd think it wouldn't be that big of a deal. But the thing is, the cell phone lenses themselves are just teeny tiny in order to fit onto the cell phone. So because they're so tiny, they can't capture that much light. So pretty much every photon that hits that lens is precious, and they have to, again, coax it towards the sensor in order to have your cell phone camera work well. All right, so let's wrap this treatment of thin film interference up with an example I was alluding to earlier. Let's say you're looking at like those shimmery rainbows that you see immediately after it starts raining in a parking lot. Not after it's rained for a good long time, but immediately after it starts raining. So what happens immediately after it starts raining, because cars have been leaking gas and oil and stuff like that, you'll have water here. And we'll just say gasoline here. Could be diesel, could be oil, whatever. And it's going to work out to be all about the same thing. Oops, here, let's move that there. Let's move that there. And at the top, we'll have air. So the index of refraction of air is about 1. The index of refraction for gasoline, so let's say air. The index of refraction for gasoline is about 1.4, and for water is 1.33. Okay. So let's say that we're interested in 500 nanometer light, so kind of greenish light coming in. And again, we're thinking about straight down. We'll be looking at it from over here. So whenever you see me draw this weird little thing, this is literally just an eye looking this way, so you can tell which way I'm thinking about the observer. So light reflecting off. Again, this is really straight up, straight down, but I'm angling it in order to make the drawing make more sense. So now some of this will pass through and reflect here, and some of this will pass through like so. Now, what I want to know is, what is the thinnest film for which it would, so if we say that the wavelength of light in air is 500 nanometers. What I want to know is, what is the thinnest, how thin can the film be that would make the surface appear bright? Okay, so here, when I take a look at this, this is going to be a case 2 situation. I can get that because I can see there's going to be no phase change here, but this is 1.4, and light here in 1.4 will be bouncing off of surface that's 1.33. So that'll have a phase change. This will have no phase change. So this is case 2. And I recommend just drawing these little cartoons really helps you figure out whether you're looking at case 1 or case 2. And since they said we want to make this look bright, that is our code word that this is constructive interference. So in that case, what we're looking at is the round trip distance will be m plus a half lambda over, now which index of refraction are we going to go for? What we're concerned about is the round trip in the gasoline, so this will be the index of refraction for gasoline here. So I can just divide through by 2 to get all the thicknesses that I could ever imagine. So this will be m plus a half lambda over 2 times the index of refraction for gasoline. So if I think about this, the problem did say what would be the thinnest. Now, since it said thinnest, what that's going to tell me is m is 0. Because if m were 1, this would be 3 halves times this. If m were 2, this would be 5 halves times this. So here, because we're asking for the thinnest, m is going to be 0. So this works out to be the wavelength in air over 4 times the index of refraction for gas. So that's going to be 500 nanometers over 4 times, we said our index of refraction for the gasoline is 1.40. So that's going to work out to be 89.3 nanometers. Now, one thing that you might start to wonder is when you look at numbers this small, I mean, this is 89 billionths of a meter. Start to ask yourself, how reasonable is that? And so just a general rule of thumb, a typical atom or molecule is going to be about 1/10 to 10 nanometers. So these are very thin films, but we can still be talking about stacks of hundreds of atoms. And so this is actually a very reasonable value. Or in this case, almost nearly 1,000 atoms. All right, so just one last note here about the oil slick in the parking lot. When you look at it, you normally see a whole array of colors, not just a single color. And why is that? And that's because of the water, the gasoline just kind of pools like this. So what this means is that the thickness is continuously varying. So here, until you get to a point where we change order, out here at the extreme edge, you'll first see blues because blue light has a shorter wavelength. So you get constructive interference from a thinner, from a shorter round trip or a thinner bit of the gasoline slick. And then that will tend over towards reds like that. And then the pattern will repeat. At some point you'll go into the infrared, but then this was m equals 0, and then we'll hit, now we can have m equals 1, and it'll be blues into reds. And eventually the patterns will start to blend together as you might be into m equals 17 for blue while you're simultaneously in 16 for red. And so you lose the rainbows after a bit. But that the fact that you're seeing, it's not really a rainbow, the fact that you're seeing these varying colors, and they might even be repeating, is showing you that, yeah, it's a very thin layer of gasoline that's on top, but you can also see that this also means it's piling up in the middle. It's thicker in the middle than it is on the edges, which is why you get the different colors. Alrighty, so in the next video, we'll go ahead and start by looking at single slit diffraction. Catch you there.